Hi, I'm Matt Kennedy. I'm a partner architect at DataStax. A little bit about me. I'm not from around here. I'm based in Washington, DC. I'm a co-organizer of the Cassandra DC meetup. I am an occasional contributor to the Cassandra project, and in case it's not obvious, I am the offspring of the unholy union of Zach Galifianakis and Nick Offerman. That was a joke to get everybody loosened up. All right, so what I want to talk about today is this term, eventual consistency. And Topshin stole a bit of my thunder along with my time, but that's okay. So it was actually Topshin and I having a conversation on chat that led to this talk. And we're basically discussing the angst that this term can cause. Because when we hear eventual consistency, especially the first exposure to it, we don't necessarily get the best kind of warm, fuzzy feelings about a system that does things eventually. And so we started talking, and we're like, well, wouldn't it be great, life would be so much easier if we just had another term, right? Let's just change the words. And because, you know, once you really get to understand the capabilities of Cassandra, you start to actually feel like there's something harmonious about how it enables different kinds of consistency capabilities. And so we came up with this harmonious consistency idea. And, you know, it sounds a little bit like marketing BS, but the idea is not that this is like some kind of slogan or, you know, doublespeak. The idea is that this is a framework for a conversation about how we can communicate to people that don't necessarily understand Cassandra all that well, to help them kind of overcome the hurdle of eventual consistency, you know, being a bit of a difficult concept to kind of wrap your head around. So Cassandra has kind of an image problem. And forgive me because I'm going to anthropomorphize here for a little bit. But there's kind of this image, because Cassandra is this eventually consistent database, that she's some kind of slacker college student that gets around to paying her mobile phone bill and, you know, doing her term papers and doing the laundry, you know, eventually when it's convenient. And unfortunately, this is an inaccurate and really wrong impression. Cassandra is, in fact, the world's greatest pragmatist. And while these rumors of her being eventually consistent are true, that doesn't really tell the whole story, right? There's much more to this story that really gives her an unparalleled worldliness and an unquenchable thirst for data. So speaking of unquenchable thirst for data, I wanted everybody in the room to be aware that there is, in fact, a big data drinking game. And I did try to avoid this talk triggering any drinking events from the big data drinking game. So watch it on video later and tell me if I'm honest. So to solve this image problem, we in the Cassandra community can't just swap out the term eventual for harmonious and call it a day. That doesn't do the job of helping the world to better understand Cassandra. Yet, if we can explain the harmony that Cassandra enables in a way that can be internalized by veterans and newcomers, then this image problem gives way to comprehension, right? Harmonious consistency isn't a marketing campaign. It's a framework for the conversation that will guide complete understanding of everything that Cassandra brings to the table. So, what's wrong with the term eventual consistency? The first problem with labeling Cassandra an eventually consistent database is that it excludes other classes of consistency for which it is capable. And we'll get to those later. And I also want to table the discussion of what exactly consistency means for a minute. Let's look at this word, eventual. So in the context of distributed computing, eventual is a term we apply to the synchronization or timing patterns of a particular system. It's an innocuous bit of jargon, right? But in the real world, where we spend the rest of our lives, it connotes laziness, passivity, and a complete disregard for anything that needs to happen on time. So like it or not, these connotations, these negative connotations, we inherently attach to the term even when we should be thinking like logic-driven engineers. And this behavior can lead to imprecise conclusions about the sort of problems to which Cassandra is suited. And worse, I think inadequate research can lead decision makers to choose strongly consistent systems simply because they sound more rigorous. So Cassandra's eventual consistency is sometimes regarded as a liability, which is very strange. Because at the same time someone will criticize Cassandra for being eventually consistent, they will, on the other hand, praise its strengths of multi-region data center capability and supporting high write rates in the face of node and network failures and partition events, right? So it makes little sense that eventual consistency should be derided as a weakness when in fact the features that are considered core strengths are completely dependent upon that. So we've said consistency a lot. Let's talk a little bit about what that means. Because in any Cassandra conference or any time people are talking about Cassandra, this word gets used. It's not possible to avoid it. So because Cassandra is a database, a lot of people think, oh, well, we're talking about the word consistency. It must be the same thing as the C in ACID, right? Because that's the consistency term that people are familiar with in the database world. But it's actually not quite the same definition. The C in ACID has to do with the state of the database being coherent at the between the start and the end of a transaction. But that doesn't really apply to Cassandra, and it's not the consistency that we're talking about in Cassandra. So in Cassandra, the consistency word that we use is borrowed more from the distributed computing landscape. And what we're specifically saying is the way in which nodes come to agree with each other on elements of data in the database. Do the nodes that make up our database have the same view of the data? So the important aspect, or the thing to realize that's kind of surprising, is that it doesn't necessarily matter to client applications that all of the nodes that make up a database agree on the state of the data, as long as the application has the ability to insist that it sees a coherent state of the data. And that is how we enable high availability and multi-region data centers in Cassandra. So this notion of an application or a client insisting to a database that it has preference on how its data is handled is sometimes this it's a very foreign concept to newcomers to Cassandra. But it's a powerful differentiator. Cassandra listens to the needs of its applications, and not just at the database or instance level, but on each and every operation performed against the database. So by taking advantage of this facility, applications can tune their consistency demands according to the logical tolerances of the application. And they can even achieve immediate consistency of their view of the data for write then read operations without sacrificing high availability. This is a strong distinction from strongly consistent systems. So more importantly, for multi-data center applications, clients can achieve immediate consistency with their local data center and let the eventual consistency capability work on the other data centers so that you're not paying geographic latencies for local, immediately consistent operations. So how does this immediate consistency work? We'll go through a detailed example in a minute, but in order to understand the concept, we need to be aware of two terms that are fundamental to Cassandra, the replication factor and the consistency level. And these are things that are sometimes conflated by newcomers. It's important to understand that the replication factor is an aspect of a key space. It's set at the database side level, and the consistency level is the per client operation setting here, right? So the two relate to each other, but they're not the same thing. And that's really important to kind of internalize for Cassandra. So to look at what immediate consistency looks like, this is a Cassandra ring, and we have writes come into a coordinator node, and we successfully write to 2 nodes out of our 3. And for our read, we successfully read from 2 nodes out of our 3. And since our replication factor is 3, and we're doing a quorum write and a quorum read, we're guaranteed that at least one node in that set of operations was the same between the write and the read. Hence, immediate consistency while still allowing, in this case, one node from each of those operations to be down. So let's look at kind of a crazier example, because I think it helps to internalize exactly what's going on. So that's a little washed out. But this is our client. This is our Cassandra cluster. So we're going to do a quorum write. And it gets to the coordinator node, and the coordinator node says, OK, I'm the coordinator node for this request. I'm going to send this write to all 5 of the nodes, but, uh-oh, 2 of them are down. But that's OK, because I get acknowledgments from the other 3 nodes, right? And so now I got acknowledgement from a quorum of my nodes, because a quorum of 5 is 3, right? So the coordinator says, I saw an acknowledgement of the write from 3 nodes. OK, I can tell the client that I succeeded. So let's look at the read side. So let's say sometime later, and this could be very briefly, but we go and read that data that we just wrote. And we see that from the last example, these 3 guys have that data that we want, and we want to get it back. And we want to make sure we get the right data back. But, uh-oh, we seem to be having some kind of serious problem with the cluster. 2 of the nodes that were involved in that quorum write have now failed. So that's not great. But what happens when we attempt the read? So we get to our coordinator node. We're doing a quorum read. And he sends the read request to 3 of the nodes. Now 2 of these guys don't know about the data yet. They haven't gotten their hinted handoff replays yet. But we got one guy that does. So he sends back the data, and now our coordinator node says, all right, I see what you see. And now I get the other responses back from the other guys, and they don't have the same data. Maybe they have an old version, maybe they don't have it at all. But because I have achieved a quorum, I had an overlapping node from both operations, I have a timestamp that says this guy wins, and now I can return the correct data to my client. So this is powerful. The client, if it chooses to, never has to see an inconsistent state in the database. That's optional. Yet the database itself can be eventually consistent. State becomes a relative concept, which is very, very powerful and is really the central reason that Cassandra is as wildly popular as it is for globally distributed applications. So having achieved immediate consistency, we might be tempted to say, well, if I've got immediate consistency, do I ever need to worry about eventual consistency? And the fact is that we do, because in the case of multi-region data centers, most of the time, we're going to want to be immediately consistent with our local data center, so we don't pay geographic latencies. And we're going to need to rely on the eventually consistent mechanisms built into the database to make sure that those other data centers do become consistent. But also, think back to the failures of the prior example. Those nodes need to become consistent, right? So eventual consistency helps us get back to a healthy state when we do have failures. But we might not care about immediate consistency. And this is especially true in, say, Internet of Things applications, where we are doing a heavy write workload into a database to capture things that are events that are happening on things. And we might never read that data. We might read only a small portion of it, and only at a much later time, when we're fairly confident that Cassandra has taken care of getting things consistent from the get-go. So in that case, we can choose to write at a consistency level of 1 just for the additional performance, right? We want to be able to sustain a very high write rate, and that's a good way to do it. So for the purposes of kind of wrapping your head around this idea of harmonious consistency, all that we really need to know about the eventual consistency tools are that they are primarily hinted handoff, read repair, and anti-entropy repair, right? And they all have really cool names and they do important jobs, but it's sufficient to know that they're there. But it's also worth talking about the performance of eventual consistency. How eventual is eventual? And this is really one of the things that I think concerns people a lot, right? If I have an eventually consistent database, does that mean that my data will get replicated to other nodes in 2 hours?
I think you hit the switch.
Oh. So, am I good?
No.
Okay. Battery.
It died?
Oh, it says battery.
Oh. I'll get the technician.
Okay. In the meantime, I will talk real loud. So, Netflix performed this experiment. And this was at Cassandra Summit last year, I believe. It's entitled Eventual Consistency Does Not Equal Hopeful Consistency. And essentially what they did, because this is important to them, they're big Cassandra users. They run in clouds that don't necessarily have the most reliable networks. They said, we want to know what happens if we have 2 Cassandra clusters in data centers across the country. And we're going to put a load on them. We're going to do 50,000 operations per second, and then we're going to do 1 million consistency level 1 writes, followed by 1 million consistency level 1 reads. Now, I think everybody should go watch the video because it's pretty good. I'm sure if you Google Netflix eventual consistency experiment before the slides go out, the link to the talk is at the bottom. But I don't want to spoil it, but they were able to read all the data in a very short amount of time. So it's eventual consistency is not something that says your data is not going to get where it needs to be. Eventual consistency allows us the flexibility to be able to deal with conditions, and the database knows how to behave under those troublesome circumstances. So, in our estimation, we wouldn't really have the ability to talk honestly about this notion of harmonious consistency if it were not for Cassandra 2.0 having linearizable consistency. So you've heard this talked about a little bit today. This is the Paxos capability, also known as compare and set, check and set. In DataStax we call it lightweight transactions, but essentially these are the CQL if statements, right? These are the consistency mechanism we have available to us to say, do this thing that I want to do if the preconditions are valid, which allows us to do one thing after another. Serializable consistency. It allows us to do these kinds of operations. Put X in the database if X is not already in the database. Set foo equal to bar if foo is some other prior value. Or even if they're in the same partition, set foo equal to bar if some other column has some other value, right? So it might not be immediately obvious why that's useful. So let's walk through an example. So suppose there's this game called Monster Mash, where players create monsters that compete to see who can mash potatoes the fastest. So the game allows players to create monsters with different attributes to help them mash faster. Each monster has a name, but it needs to be unique. It goes without saying that this is the most popular game in the world, so it absolutely has to use Cassandra for its database. So now suppose two players, Alice and Bob, want to create a monster named Stinky, right? So they've designed Stinky, they figured out, how Stinky's going to mash potatoes the fastest. And now, so this is prior to lightweight transactions, and we'll show lightweight transactions next. So they need to check with the database and say, hey, can I create Stinky? Does Stinky exist? And they both ask the database at roughly the same time. Database says, no, Stinky doesn't exist. You can go ahead and create Stinky. So now Alice does a quorum insert to create Stinky, and Bob does a quorum insert to create Stinky. And Alice, for a second there, owned Stinky. She was happy. She got to create her monster with her great name. But Bob now came along afterwards and squashed Alice's monster. So now Bob owns Stinky, and Alice doesn't know why she can't see the monster she just created. So let's look at the alternative. So we've got Alice and Bob, they create Stinky. Does Stinky exist? No. Insert Stinky with a lightweight transaction insert. So what Alice is doing is saying, insert my values into my table where, if this row does not already exist. So insert Stinky if Stinky does not exist, basically. And Bob does the same thing. He says, also, insert Stinky if Stinky does not exist. But since Alice already succeeded with the lightweight insert for Stinky, Bob gets a sad face. And he does not get to name his monster Stinky, but we don't have the confusion created in the prior example. So this is a new feature in Cassandra 2.0, but I believe, in keeping with the consistency strategies that we've had around for a long time. And it saves us from having to do tricky things like worry about the consensus algorithm at the application server level, or say use Zookeeper to do some kind of locking on these operations. So, check the time. We have a break after this, and I think people are got afternoon weariness. So I am going to go through this pretty quickly. Let's look at some cool things that you can do because of these consistency capabilities. So this is a Cassandra data center. Data centers can go offline at any time for a variety of reasons. And we need to be able to deal with the fact that data centers go offline, right? What happens if I've got 3 data centers and I lose one? Well, your applications can immediately route to the other data centers and you're good to go. But, oh, I was in New York. I messed up. I changed my slides around because I didn't want the lightning bolt to be going on New York while I'm in New York. I figured that was a bad omen. But I forgot to change all the slides. So anyway, so let's say we've lost a data center, and our application is able to go to the other data centers, but maybe we're seeing some higher latencies now, right, where we need extra capacity. So rather than build another data center, we can go to the cloud, and we can make the cloud data center connected to our on-prem data centers. But what's even more interesting with clouds is, we can span cloud availability zones, but we can also span cloud to cloud, which is a pretty interesting capability in case you don't want to get tied into a particular cloud vendor. But then the other thing that seems to be really popular is the ability to go cloud to on-prem for both, either having a cloud data center as part of your core capability, or for migration off of clouds once the expense just becomes a little bit too much to bear. So, wrapping up, tunable consistency, linearizable consistency, your application tells Cassandra what it needs. This is really important. The consistency mechanisms in Cassandra make Cassandra what it is. All of her core strengths are dependent on the consistency model. High availability, tolerance of node failures, data center failures, network outages. And a network outage doesn't have to be like a transatlantic cable cut, right? It can be, there's a lot of traffic, and my ping times across the country are too high for my requests to finish within the timeouts, right? Network partitions take on all different forms, and having the flexibility to deal with bad network weather is really powerful. So essentially, we're making the argument that we can help people understand the reality of eventual consistency as a not necessarily scary term if we can clearly explain everything that goes in behind that, right? And so that's why I think that harmonious consistency is a useful framework for that conversation. So, takeaways. Consistency is a key value. It's a NoSQL joke. Thank you. The reality of today's applications, always on, globally spanning applications, need multi-region DCs. Multi-region DCs must face the reality of network partitions. So harmonious consistency enables applications built on Cassandra to do what they need to do correctly and flexibly while remaining highly available. So, that is it. Any questions?